This conference will now be recorded.
Hello everyone. We have started heavy water already and we have seen chemical reactions and some properties, physical properties, and we will finish it with uses of heavy water, and after that there will be some related problems. And once it is finished, then we will start hydrogen peroxide, which is another oxide of hydrogen, and the structure of hydrogen peroxide, its physical properties, how we can prepare it, all these things we will discuss today. So uses of heavy water. So heavy water means D2O. Fine. So this is heavy water. Now it is commonly used as a tracer to study organic reaction mechanism. We know that when we break the oxygen-hydrogen bond of water molecule, then the bond energy, and when we break the D-oxygen bond, then the bond energy, both are not same. So to break the HO bond, it is comparatively easier, but to break oxygen deuterium bond, it is comparatively difficult. So that is why if we want to check whether any oxygen hydrogen bond is involved in the mechanism or not, that is breaking of HO bond is involved in mechanism or not, to test that, what we can do, instead of taking water molecule, we can take D2O molecule, so that we can understand whether there is any difference in rate. Because if bond cleavage of HO bond, that is hydrogen oxygen bond, if it is involved in the rate determining step of the reaction mechanism, then obviously when you are changing it to from H2O to D2O, there will be some difference in rate, and if difference in rate is observed, it proves that obviously this HO bond is involved, HO bond cleavage is involved in the rate determining step of the mechanism. Then heavy water is used for the preparation of deuterium also. Last day we have seen different chemical reactions of heavy water, and we have prepared some deuterium containing compounds. So just for simple example, H2SO4, suppose I want to prepare D2SO4. That is, these two hydrogen I will replace with D. So for that purpose, what I can use deuterium as the source of, that is, I can use heavy water as the source of D. So it can help us for the preparation of some deuterium containing compounds. Then heavy water is widely used as moderator in nuclear reactor. If you consider the nucleus of heavy water, obviously here number of neutrons are high compared to hydrogen nucleus. So that is why, because of this difference in neutron number, it is widely used as a moderator. That means it can control these nuclear reactor reactions, because these reactions, they are very vigorous, and once we use heavy water, it can moderate the reaction speed. So it can lower the energies of fast neutron, because here difference in number of neutron is observed for D and compared to H. It is also used as a coolant in nuclear reactor because it can absorb the heat generated. Fine. So these are the uses of heavy water, that is D2O. Next we will see, we have a problem here. So in this problem, it is saying that statements about heavy water, there are some statements related to heavy water you can see. So heavy water is used in exchange reactions for the study of reaction mechanism. This is the first statement. Then the second statement is saying that heavy water is prepared by exhaustive electrolysis of water. Then heavy water, it has higher boiling point than ordinary water, and viscosity of water molecule, that is greater than D2. Fine. So among these four statements, we have to find the correct statement. So here correct statements are A, B, C, then AB, then AD, and AC. That means in all the options we have A. So A is actually true, because we have just discussed the uses of heavy water, and there we have seen that heavy water is used in exchange reaction for the study of reaction mechanism. So this is one of its applications. So this is true. Then heavy water, how it is prepared, in the last class we have seen it is by exhaustive electrolysis of water. Exhaustive electrolysis means you have to do the electrolysis for a long time. It is also called prolonged electrolysis. So this is also a preparation method. That means B is also true. Heavy water has higher boiling point than ordinary water. Now the physical properties of H2O, D2O and T2O, all this I have already mentioned in a table, not in the last class, maybe the class before that. And they are all the physical properties. That is boiling point, melting point, viscosity, polarity, everything is we have seen the comparison. And here we have seen that heavy water, it has higher boiling point than ordinary water. This is actually true. But what about the last statement? Viscosity of H2O is greater than that of D2O. Is it true? So basically, it is not true. It is incorrect. Viscosity of water, it is not greater than D2O. Basically, the viscosity of D2O is high, which is clear from its value. Though the difference is not very high difference, but still it is greater. That is for D2O, it is greater. So that is why correct statements will be only the first three statements, not the last one. Okay. So basically A and B, if we are sure, then you can easily cancel these two. Now among these two, we just have to know that whether boiling point for heavy water and ordinary water comparison, which one is high. Once we know that, then we can choose between 1 and 2. How and why does the density of liquid water change if we do prolonged electrolysis? It is observed that when we continue the electrolysis for a long time, then the density of liquid water changes. Now, what is the reason behind that we have to find here? The first statement is saying as a reason that it decreases. How and why? So first of all, you have to mention whether it is decreasing, remaining unchanged, or increasing. So three possibilities are there. So that is how. And then we have to answer, why does the density of liquid water change if it is changing? Now it means obviously it is changing. So option B is not correct. Okay, it is either decreasing or increasing. Now the first logic in the statement is, it is given as it is decreasing because the proportion of H2O is increasing. Now when we are basically doing electrolysis of water, now some percentage, very low percentage of H2O, there is D2O also. Now obviously first H2O will be undergoing electrolysis, and the amount of H2O that will gradually decrease. It will not increase. Fine. So next statement is already not correct. Then option C is saying increases as the proportion of D2O increases. And the last option is saying this is also increases, but as the volume decreases. So the reason is different. It is just like option C, but reason is different. It is saying that proportion of D2 increases, but here it is saying that volume is basically decreased. But which one is actually true, that we have to know. So see, volume is decreasing. This you cannot say correct because it is overall volume is decreasing. So when you are taking a particular portion of this whatever volume you have started with, in that amount density it will remain same. So basically here volume decrease, this sentence doesn't make sense because we have not taken any solution. It is not that we have taken some solute, we have dissolved it in some solvent. It is not like that. It is simple water. So volume decreases, density increases. This type of logic we cannot give. So what is actually happening? On prolonged electrolysis, density of liquid water increases. The actual reason is the proportion of D2O is increases because only some percentage is D2O. But as first among these two, H2O will undergo electrolysis. So gradually the amount of H2O will decrease and the amount of D2O will increase. Now as molar mass of D2O, it is obviously higher than H2O because mass of D is high. So that is the reason that when proportion of D2O is increasing, mass is increasing, right? So this is because on prolonged electrolysis, concentration of heavy water in liquid water increases, and it is having higher density that you can find in the table that I have already provided. The density difference comparison basically among H2O, D2O and T2O. There you can see it is having higher density than ordinary water. So electrolysis you are continuing for a very long time, then almost you can get pure D2O, and this is actually the process of exhaustive electrolysis by which you can prepare D2O. But it is also giving you the answer that why density of liquid water is increasing. So the answer is basically proportion of D2O increases, and this method is also the preparation method for D2O. So that is the correct option, option C. Next we will go to next question. Incorrect statement, or it may be more than one, about heavy water is and are. So we have total 4 statements, and see option 1, 2 and 3, there is only one statement it is saying that correct, B, C or D. Only in the last one it is two statements together. Choose the correct answer from the options below. We have to find the wrong statements. The first statement is saying it is used as a moderator in nuclear reactor. So this information we have just seen in the uses application part of D2O. So it is correct, obtained as a byproduct in fertilizer industry. Now this is basically a preparation method that we have discussed in the last class. So there we have seen that it is one of the method by which we can produce it. Then used for the study of reaction mechanism, right? Has a high dielectric constant than water. Now it is also true that we use it in the reaction mechanism, we have seen in the application part. But what about dielectric constant? Remember, you have to use the same table. So that is why I am saying again that the comparison table of physical properties of H2O, D2O, T2O, study that table very carefully, because related to that table you may get many questions. You can see that here. Dielectric comparison we have to do. Higher dielectric constant than water. That means D2O. Is it having higher dielectric constant? No, it is not having higher dielectric constant. Okay. H2 is having high dielectric constant because the polarity of this molecule, it is obviously high, and when polarity is high, dielectric constant, that is also very high. So that is why this is not correct statement, and we have to find wrong statement. So incorrect statement about this heavy water, this is basically the fourth statement, D. That means option 3, which is where it is mentioned that D only, that we should choose. Which one of the following statements about water is false? Water is oxidized to oxygen during photosynthesis. Then water can act both as an acid as well as it can act as base. There is extensive intramolecular hydrogen bonding in the condensed phase. Now see, it is saying that intramolecular hydrogen bonding. Intra means within the same molecule hydrogen bonding. But hydrogen bonding, what we have seen, it is basically, if I draw two molecules, so one, that is oxygen of one water molecule, it will interact with hydrogen of another water molecule. So basically it is hydrogen bonding between two different individual molecules, and there are many water molecules you can draw. I have just drawn two. So it is not intra, it is inter, right? So this should not be correct. And the last one, ice formed by heavy water sinks in normal water. Now this is also true, and this information we have already seen in previous classes. So if we take normal, that is ice made of normal H2O, and then you are keeping it in water, obviously it can float. But it is not the case if you take ice which is made of D2O. Okay, so in that case it will sink because density is high. So there is extensive intermolecular hydrogen bonding in the condensed phase instead of intra. So this is not correct. Basically this is false, and you have to choose false. Ice formed by heavy water sinks in normal water, and the explanation is heavy water is slightly more massive than regular water molecule, and heavy water molecules may pack more closely than regular water molecules. So this information is not new, we have already seen it, but again for this question, here the explanation is given. So it is option C, which is false. And the other two statement, water acts as both acid as well as base. It depends on what is the other compound. So if you take acid, suppose you have taken HCl with water, then water it will act as base. It will take proton from HCl. But if you are treating water with ammonia, now ammonia will take proton from water. In that case, water is behaving as acid, and water is oxidized to oxygen during photosynthesis. Now water, if it is converted to O2, that means what? Here it is basically oxidation. Here oxidation, it is oxide, that means charge is -2, but here it is carrying 0 charge. So it is obviously oxidation. Fine. So option C is the correct option. So now we will start the next topic, which is hydrogen peroxide. So hydrogen peroxide, it is also oxide of hydrogen, just like H2O, but only difference is here you have one oxygen extra, and this is the bonding. That is, you have HO, then OO linkage. So this is a unique thing you are seeing here, which you have not seen before. In water, it is HO and then H, but here we are seeing OO linkage. Like H2O, hydrogen peroxide is another hydride of oxygen, which is containing this unique type of bond. This oxide is pale blue, clear liquid, slightly more viscous than water in its pure form. So if you look at this compound from far, you will not be able to differentiate between these two. But if you look closely, then obviously you will be able to understand the difference. Unlike water, it is thermodynamically unstable. So compared to water, it is unstable. Therefore, decomposes to water and oxygen. So there is a tendency of this molecule that it decomposes to H2O molecule and oxygen molecule. Obviously, if you want to balance it, you have to take 2, and here it will be 2 also. Then both sides it is balanced. Fine. So this tendency is there. That is decomposition tendency, because it is not thermodynamically stable like water. So this is also the property which you have not seen in case of water, but here it is present. Next we'll see as established by X-ray studies, the molecule has non-planar structure. Now its structure is very unique, and related to this structure you should study this very carefully, because its structure related questions are very common. The molecule has non-planar open book type of structure. Suppose you are opening a book, don't fully open it. Suppose you have opened it 90°, then you can find some similarity. So it is non-planar open book type of structure. So look at this. So as if we have opened a book. So this is one side, this is another plane, basically 2 planes as if. So the angle, as you can see, between these two, 111.5. But this angle when it is in gas phase. But if it is in solid phase, now the angle reduces to 90.2°. So it is different. Otherwise it is that is more or less close to 90°. There are 2 planes, and each plane has one OH bond. So here you can see this OH bond, it is in one plane. OO bond is here, which is common to both of them, and another OH is here, right? The O linkage is called peroxide linkage, OO, and both in gas phase as well as liquid phase, the molecule adopts Q conformation because of repulsive interaction of the OH bonds with the lone pair of electrons that is present on each oxygen. So see, if I draw it here, each oxygen is basically carrying lone pair. Now this bond pair and lone pair, there is some repulsion. Now suppose if both the hydrogens are on the same side, that is in the same plane suppose, then this repulsion, it will be high. So that is why this structure is not actual the correct structure. This is the correct structure. So both in gas phase and liquid phase, you can find some similarity, though there is some difference in the lengths. As you can see here, it is 95 pm, that is this OH bond, and this OO linkage is 147, but when it is solid phase, it is slightly different, right? And also this angle OOH, it is 94 here, and in this case, as this angle it is slightly reduced, and also this angle is slightly increased. So these are the little difference between the structure, whether it is in gas phase or solid phase. So the common point is the molecule adopts Q conformation. So this type of structure, that is open book type of structure, it is Q conformation due to the repulsive interaction of the bond pair electron, bond pair of which bond? OH bond, with the lone pairs of the electrons that are present on each oxygen atom. Now when it is in the crystal, that is a solid form, the dihedral angle, this is very important information, the dihedral angle, it is decreasing from 111.5 degree to 90.2 degree. So this is important difference, which is unique and related to this. We may get question. So this is important information. And why it is so? It is because of hydrogen bonding. Because when you are moving from gas phase to solid phase, now the molecules, they are close to each other. So hydrogen bond formation, now the process is more facile compared to the gas phase, and because of this, now these two planes, they are close to each other. So the angle between these two planes, which is also called dihedral angle. So this term dihedral angle, it is not for H2O2, it is basically a common term we use in organic chemistry also we use it. So when we have this type of two planes, the molecule, suppose one bond is one plane, another bond is another plane, this type of angle between these two planes that are connected by this bond, we call it dihedral angle. Okay, so these are the structure related informations. Next we will see preparation methods. Preparation methods for H2O2, but we have classified it. The first we will see, it is laboratory method. Laboratory method is obviously small scale method that you can call laboratory method. So in laboratory, what we can do for preparation of H2O2. So the first method here we are seeing from sodium peroxide. It is also known as Marx process. Now sodium peroxide, it is basically, what is the formula? It is Na2O2. If I am saying simple sodium oxide, the formula is different. The formula is Na2O. But when I am saying sodium peroxide, the formula will be Na2O2. It is just like H2O2, as if you have replaced two hydrogen with two sodium. That is the only difference. So in this technique, what we do, calculated amount of this compound Na2O2 is gradually added to an ice cold solution of 20% sulfuric acid, and that is also covered by ice. So temperature, see, temperature is low here, covered by ice, and regularly starting regularly, it is important, so that the heat, if it is generated, it is distributed. So that is why starting is important. So Na2O2 reacting with H2SO4, it is producing H2O2, that is the actual compound. Our focus is to produce it, and this is the byproduct. Now what will happen once the reaction is done? This byproduct, sodium sulfate, it will form crystal with 10 molecules water of crystallization. It will be associated with it, and it is separating out as the solution is cooled. So when Na2SO4, it is well soluble in water. So gradually when your, that is temperature is decreased, its solution is cooled, so its solubility will decrease, and you can see the crystals are coming out. And when the crystals are coming out, that means the remaining clear solution, that is basically H2. And this is 30% H2O2. Now H2O2, its concentration is basically expressed in two different ways that we will discuss probably in today's class or next class. It is basically expressed in two different ways. One is percentage, another one is volume. So in this case, you can see it is expressed in percentage. So 30% H2O2. Details of this how to express the concentration of H2O2 that we'll see later. Right now, just see, we get 30% H2O2 for Marx process. And the crystals that you are getting for this molecule, sodium sulfate 10 water molecule, that we can separate by filtration method. Okay. So laboratory method, Marx process, which is involving the substrate Na2O2 and H2SO4 as the starting material. Next laboratory method is barium peroxide. Now when we are discussing it under the heading from barium peroxide, don't think it is a single method. Basically under this 2 to 3 methods will be there. So the first method you are seeing in this slide. So what we are doing, a paste of hydrated barium peroxide. Barium peroxide, look at the formula, it is BaO2. If I am saying normal barium oxide, the formula is BaO. Ba, we know it is group 2 metals. Oxidation state of group 2, obviously it is 2 plus, and this oxygen, it is carrying 2 negative charge. So that is why the formula is BaO. But when it is peroxide, basically 2 oxygen atom carrying this 2 negative charge. Fine. So it is like this. If I elaborate it, it is like this. Or you can write it like 2 negative. So O2 is carrying 2 negative charge. So that is why the formula is now BaO2. So per oxygen, it is basically -1 charge. So this is the difference in formula, whether you are talking about barium oxide or barium peroxide. So here we have taken barium peroxide, BaO2, with 8 water molecules attached. It is a paste of this molecule is prepared with ice cold water. And then this paste, see, it is paste, it is not solution. It is prepared with ice cold water and then it is added slowly to an ice cold solution of 20% H2SO4. So again we have taken 20% H2SO4, which is ice cold solution. In the previous case also, Marx process, we have used ice cold solution, and so that because there is a chance that H2O2 can be decomposed. So we have to, once it is we are obtaining is at product, we have to take care of the fact that it is not further decomposed. It is prone to decomposition. So that is why this temperature maintenance, ice cold solution, this should be taken care of. So BaO2 8H2O, then plus H2SO4. What we are getting H2O2 obviously, because that is the main product we are trying to produce. But we are also getting BaSO4 solid, which will be precipitated because its solubility is very low, and water will also be produced as byproduct. Now this precipitate of BaSO4 we can easily remove by filtration. Now it is good for us because these are the byproducts, we have to remove it. We just want H2O2, we do not want the other products. So to remove these undesired products, we can easily do filtration because it is not soluble. You can get PPT, you can remove the PPT by filtration. And you will be now left with 5% solution of H2O2, dilute solution. So these informations are important. When it is Marx process, you are getting 30% H2O2. When it is this barium peroxide method, you are getting 5% H2O2, right? Now this method, we have some limitations. So what are the limitations we are facing here? H2O2 prepared by this method, it contains appreciable quantities of Ba2 plus ions. Now these Ba2 plus ions, now it can catalyze the decomposition of H2O2. As I was saying that H2O2, it is prone to decomposition. So that is why we have to take care of the fact that whether that is the H2O2 that we are preparing, it should not be decomposed. Okay, otherwise all whatever we are doing, that will be meaningless. So to prevent that, what we can do, that is this method, it is not very good for it. Fine. Now Ba2 plus in the form of dissolved barium persulfate. Barium persulfate is BaO8H2. Detailed structure you don't need, just remember here in this method we have some Ba2 plus and these ions, it is catalyst for the decomposition of H2O2. So the H2O2 that will be produced, we cannot store it for a long time. So this is the drawback of this method compared to the previous one, right? Now barium peroxide, this is the first method. Some more methods are also there that we can do from barium peroxide. So from barium peroxide, the second method here you can see when a rapid stream of carbon dioxide is bubbled through a thin paste of BaO2 in ice cold water. So the same thing again, we have made a paste, but now we are that is we have taken a rapid stream of CO2 is bubbled. In this case H2O2 is produced. In the previous case we have taken H2SO4. Now we have taken CO2. So we are getting BaCO3. In the previous case we have obtained BaSO4. Now we have obtained BaCO3. Now this will also be precipitated and H2O2 is the byproduct. Now the insoluble barium carbonate, this is just like BaSO4 insoluble, so you can easily remove it by filtration, leaving behind a dilute solution of H2O2. So the same method you can remove the other product so that we can get H2O2 only. Then the third method, another method is also there by the action of phosphoric acid. So see, BaO2 is common. In the first case we have taken H2SO4 as the second starting material. Then in the second method we have taken carbon dioxide, and in the third method we have taken phosphoric acid H3PO4. So depending on what you have taken as a second reagent, that is whether it is CO2, H3PO4 or H2SO4, depending on that you will get the other product BaSO4, BaCO3, and in this case you are getting Ba3PO4 whole 2. Now PO4 ion is basically carrying 3 negative charge. So to balance 3 negative charge, here we have 3 barium 2 plus. The total positive charge 3 into 2 plus 6 plus. Here total negative charge, you have 2 phosphate, that means total negative charge minus 6. So that is why the formula is like this, Ba3PO4 whole 2, and this will also be precipitated, you can remove it, and H2O2 we are getting. Now this method, it has some advantage compared to the previous, that is the first method. Remember in the previous slide we have seen BaO2, we are treating it with H2SO4 and we are getting BaSO4 precipitate, we can remove that, right? But this method has advantage over BaO2 H2SO4 method since almost all the heavy metal impurities that is present in BaO2 and it is responsible for catalysis of the decomposition of H2O2. So all the impurities present in BaO2, heavy metal impurities that are present in BaO2, they can be removed as insoluble phosphate. As a result, the H2O2 solution produced has excellent storage qualities. So not just Ba2 plus is catalyzing, sometimes some heavy metal impurities are also present that can also act as catalysis. But those impurities, as we are now using phosphate ion in the medium, those heavy metals, they can form phosphate salt and they will be removed. When you are removing this compound by filtration, then those heavy metal impurities are also removed because they are also insoluble, unlike the previous H2SO4 method. So that is why this method with H3PO4, it is better than the other one. So after laboratory method, next is industrial methods of preparation of H2O2. Industrial methods of preparation, that means now it will be large scale preparation of H2O2. That is industrial method. So electrolysis of 50% H2SO4. You know, electrolysis of water, but now instead of taking water we have taken 50% H2SO4. Okay, this is the concentration. H2O2 is manufactured by the electrolysis of cold 50% solution of this in an electrolytic cell where the electrolysis will take place. Platinum is the anode. These informations are important because you may get MCQ question that which is used as cathode, which is used as anode. So then you can answer it. Okay. So platinum is anode, graphite is the cathode. So this is the electrolysis. When we are talking about H2SO4, obviously there will be the cation H plus and HSO4 minus, that is the anode. Now this H plus at cathode, we know at cathode there is reduction. So this proton, it will accept electron at cathode, it will be reduced to hydrogen gas. And at anode, this HSO4 minus ion, it will be converted to, we have two HSO4, so it will be converted to H2S2O8 and 2 electrons will be removed. So here basically oxidation is taking place, and that is normally that happens, reduction at cathode, oxidation at anode. But if you consider the overall reaction, this is peroxide disulfuric acid, H2S2O8. This formula, the name is peroxide disulfuric acid. So the 2 electrons that are produced here, that will be used up in the cathode. But overall equation, if we write, what we will see, we will get H2S2O8 as if it is reacting with water, because what we have taken 50% solution. So water will also be there. So this H2S2O8 that is produced at anode, it will react with water and it will produce H2O2 and also sulfuric acid. Now, what we'll do next, that we'll see here. So this peroxide disulfuric acid, H2S2O8, which is formed at anode, as you can see in this equation, is withdrawn and then that is, it is separated from anode and then distilled with water under reduced pressure. So when it is undergoing the distillation, it will basically react with water and it will produce H2O2 and H2SO4. Now as H2SO4, its boiling point is low, we'll also see its boiling point, melting point, all those properties. So as its boiling point is low, it will first distill, because that is the ultimately when you have taken this mixture of H2S2O8 and H2O in the distillation flux and you are heating it, they are already converted to two liquids. One is H2SO4, another one is H2O2. Now distillation is the method based on the principle, the liquids that are trying to separate, their boiling point should be, they should differ from each other. So the liquid which is having low boiling point, it will come first because it is more volatile. And that is why H2O2 compared to H2SO4, it is having lower boiling point, so it will distill over along with the water, that is H2. Water is also present in the medium. H2O2, water is there, H2SO4 is there. So H2O2 distill over along with water. That means H2O2 and water, this mixture, it will be distilled to the right hand side. If you just remember the setup of distillation, we have some distillation flux in the left hand side. Suppose this is the distillation flux in the left hand side, we are giving heat and then this vapor is coming out, there will be a condenser where water will be, that is cold water is supplied, that is there is inside there is another tube, and finally it is stored in some another container. Okay, so here this H2O2 solution that will be stored, so leaving behind high boiling H2SO4. So H2SO4, it will remaining in this distillation flux in the left hand side, and you can recover it and recycle it, because H2SO4 is also another important compound. So nothing is wasted. Fine. This is the electrolysis method, industrial method for preparation of H2O2. The next industrial method, auto oxidation of 2-ethyl anthraquinol. So we have to see the structure of this molecule. What is 2-ethyl anthraquinol? Now there is anthracene molecule, which is basically hydrocarbon. From anthracene, this is basically a derivative of anthracene. So in this process, first of all, look at this molecule. So anthracene is 3-benzene ring fused. So in anthracene now at 2 position, this is 1 position, this is 2 position. At 2 position there is ethyl group and also at these two position 9 and 10, there is 2 OH hydroxide group. Okay, so this is the structure of 2-ethyl anthraquinone. Anthraquinone is, you can say, as if it is this compound. As you can see, anthraquinone in the second structure, that is after the reaction, whatever structure you are seeing, this molecule. Now the middle ring, it is no longer aromatic, and we have these two C double bond O. So this molecule is called anthraquinone. But if we have a ethyl group at these two positions, this is two position, then the name will be 2-ethyl anthraquinone. But what is happening here? See, in the left hand side you have 2OH group at 9 and 10 position. These two positions are 9 and 10 position. But once you are treating it with oxygen molecule, which is written on the arrow, now it is converted to 2-ethyl anthraquinone. That means O2 is acting as oxidizing agent. Now O2 we normally directly do not use. What is done? Air is bubbled through a 10% solution of this 2-ethyl anthraquinone in benzene and cyclohexane. Benzene cyclohexane is basically solvent. It is not taking part in reaction. So air is bubbled, and air is basically the source of O2. We are using air because we just want to use the O2 which is present in the air. It is bubbled through 10% solution of it, and now this 2OH group, there is this part, that is a 9 and 10 part, these 2OH, now see these hydrogens are removed, and we are at these two positions. Now we are getting C double bond O. So this is basically oxidation happening. We are getting anthraquinone. But what is H2O2? H2O2 is basically, that is our main motto to produce this compound, that is substrate from which we are producing H2O2, but H2O2 is the actual product. So H2O2 is present in the right hand side, that is the main product, and along with you are also getting these two anthraquinone. But the beauty of this reaction is, if you look at this reagent H2PD, now you can move backward. Suppose H2O2 you have already obtained, just remove it, separate it. But the anthraquinone moiety, again you can do some reduction. So H2O2PD, it is reducing agent. So again this C double bond O, these two groups, now it will be converted to COH. So this is reduction. This side oxidation, and the reverse direction, it is reduction. Fine. So first it is oxidized to 2-ethyl anthraquinone, H2O2 is formed. Now H2O2 thus formed, it is 1%. See, we are always expressing it in terms of percentage. So it is always in solution. Remember in Marx process we have seen it is 30%, then we have seen it is 5%. Now we are seeing it is 1%. So very dilute solution. So if you are a little bit confused, don't worry. Basically we'll also discuss how this percentage, that is how H2O2, its concentration is represented. Detailed discussion, separate discussion will be there. Right now, just focus on this. H2O2 thus formed about 1%. It is extracted with water, and the aqueous solution is concentrated by distillation process under reduced water, so that now the concentration is increased from 1% to 30%. So this is by wet H2O2 solution. So if the question is asked that the final H2O2 that we are getting in this process, which is 1%, how we can increase the concentration? It is through distillation process. Finally, this 2-ethyl anthraquinone, quinone basically, this 2-ethyl anthraquinone, we can reduce it again by using H2PT to the starting material, so that you can use it again. So nothing is wasted. Fine. Preparation of H2O2 is done. Now storage of H2O2. Now see, this is something we have not discussed for any other compound. We have previously we have discussed many compounds. We have seen how to prepare H2O, and then there is nothing related to storage. But here we are discussing storage of H2O2 because this compound, there is some stability issue. So it is not that you are keeping it as it is. and it will remain stable. No, it is not like that. So you have to store it with proper care. There is some how to store it, basically we will see now, because there is a tendency to decompose. So as it has tendency to decompose, just follow this equation: 2H2O2 converted to 2 water molecule, 1 oxygen. And when it is triggered, it is triggered in presence of light, and it is catalyzed by some metal surface. So traces of metal impurities should not be there. And also it is catalyzed by traces of alkali present in glass container. Suppose you are storing it in some glass container, and sometimes traces of alkali is also present in that, and that is the issue. So we cannot store it in glass container, and in glass container as it is transparent, so it will be exposed to light. So glass container not allowed. Because of this property, concentrated solution of H2O2, it can be dangerous if you are not taking proper care, because there will be uncontrolled rapid decomposition leading to explosion. So what to do? It is stored in waxed lined glass plastic container in dark. So glass is fine, but it is should be wax lined. That is specially prepared, but mostly it is kept in plastic container, and better if it is a dark color plastic container, and never it should not be exposed to light. These are the precautions we should take. Small amount of stabilizer like phosphoric acid, urea, glycerol, sodium citrate, all these molecules must be added to retard its decomposition. So catalyst, some catalyst, that is metal impurity, metal surface, it can act as catalyst for this decomposition. But there are some compounds also that can act as, that can play the reverse role. That is, it will act as stabilizer. Phosphoric acid, urea, glycerol, sodium citrate. Some of this structure you can see here. This is the structure of glycerol. This is sodium citrate. I'm not saying that you have to remember it. Glycerol is simple structure, but in case you are interested, so that is why I have presented the picture. Urea is basically NH2CONH2, and phosphoric acid H2PO4. So these are the molecules that we can use as stabilizer. Physical properties of H2O2. Pure state. If it is pure state, almost colorless, very pale blue, syrupy liquid. So it is slightly viscous compared to water. So if you look closely, if you have taken in one container water, another container H2O2, you can differentiate by looking closely. It has odor like that of HNO3. So this is another property by which you can differentiate. Its aqueous solution has bitter taste. Obviously we cannot taste it, but this is the its taste, which is bitter. Soluble in water. So that is why we are always talking about 30% solution, 5% solution. If it is not soluble, how we can say so? But also soluble in alcohol and ether in all proportions. Density, C, 1.44. Density is more than water. It is syrupy liquid, so density is high. And why it is so? It is due to association of its molecule by intermolecular hydrogen bond. BP and MP, boiling point, melting point, 423. Now 423 Kelvin, if you convert it to degree centigrade, it will be 1550 degrees. That means it is not very high, that is not very high boiling point, not very low also, but not very high. And 272 Kelvin, that means its melting point is 0 degree, near close to 0 degree. It decomposes vigorously when you are heating. That is, there is a chance of decomposition. That is, we have already seen this fact. Now that is the reason, if you directly want to determine its boiling point, suppose you are boiling it to check its boiling point. At you have set some thermometer, you are trying to boil, but what will happen? As it is, there is a chance of it is vigorous. It will lead to explosion. So that is why in this way you cannot measure boiling point. This is not so direct method. So there are some special methods which is known as extrapolation method, by which boiling point can be determined. Because if we want to determine boiling point, just we can do for other liquids at atmospheric pressure, it decomposes vigorously, so it will lead to explosion. So that is why direct method boiling point we cannot determine. It should be done with extrapolation method. Dipole moment of H2O2, it is little more than water. So this is another important information. Fine. So percentage strength, as I have said already, that strength of H2O2, it can be expressed two ways: percentage strength and volume strength. Percentage strength we have already seen. Sometimes we have said it is 30%, sometimes 5%. So now we will see what it actually means. Percentage strength. Suppose I am saying X% of H2O2. What it means? It expresses the amount of H2O2 by weight that is present in 100 ml solution. So when I'm saying it is 30%, or suppose I'm saying it is X%, that means that particular sample of H2O2, if it is 100 ml solution, there must be 30 gram of H2O2. Or if it is X percentage, there must be X gram of H2O2 in 100 ml solution. So this is percentage strength. But the common way by which it is expressed, that it is more common compared to this, that is actually volume strength. So concentration of H2O2 solution is expressed in terms of the volume of volume of O2. Remember the equation? You have already seen it. Again, I am writing it. 2H2O2, when it is decomposed, you get 2 water molecule and 1 O2. That means from 2 H2O2, 2 moles of H2O2, you are getting 1 mole of oxygen. Now, oxygen gas we are getting, 1 mole oxygen gas we are getting from 2 moles. The concentration of H2O2 solution is expressed in terms of volume of O2, which a solution of H2O2 produces on decomposition at NTP condition. So at NTP condition, if you have taken some H2O2 solution, and if suppose it is labeled as 10 volume, suppose in the bottle it is labeled as 10 volume. So what it means? It means 1 ml of such solution of H2O2 on decomposition, obviously at NTP condition, not just any condition. 1 ml of such H2O2 solution on decomposition will produce 10 ml of O2. Okay. And if I am expressing it in 1 liter, then also it is just 10 times high. So if you have mentioned it as 1 liter, then you also have to mention it at 10 liter. But because see, when I'm saying 10 volume, there is nothing, no unit mentioned. Liter, ml, nothing is mentioned. So 10 volume means if you have started with 1 ml H2O2, you will be getting 10 ml O2. If you have started 1 liter H2O2, you will be getting 10 liter O2, 10 times high. That how you know if it is written as 10 volume. The solution of H2O2 sold in the market, they are labeled as 10 volume. So these are some normal volume strength 10 that are available in the market: 10 volume, 20 volume, 30 volume, etc. Now, a 30, if we combine these two methods, what will happen? A 30% solution of H2O2 is marketed as 100 volume. So that means what? When a solution you are expressing in percentage strength, then you are saying it is 30%. But this is also equal to 100 volume. That means these two are equal. But how these two are related, how you can convert it, obviously we will see that. So it means that at NTP, 100 ml of O2, 100 volume means what? From 1 ml of this solution, 100 ml O2 will be liberated. That is the definition of volume strength. Now, when it is 30% percentage strength, then volume strength is 100. That means when it is 10 volume, see, instead of 100 volume, if it is 10 volume, now the percentage is also decreased 3%. You have reduced 10 times, 100 to 10. This is also reduced 30 to 3. So we will see how we can convert it. Today we will not be able to finish it. And once you complete all the process, strength of H2O2, solve some problem, the idea will be clear. So suppose we want to convert. Here it is, this topic is calculation of strength of H2O2. Suppose you want to convert volume strength to percentage. So you have been given a sample where in the bottle it is labeled 10 volume, and you have to convert it to percentage strength. So how to do? Obviously it is at NTP, then only the 10 volume that is applicable. Now 10 volume H2O2 means what? At NTP 100 ml of O2 will be liberated on decomposition of 1 ml of this solution. Okay, sorry, 10 volume H2O2 means not 100, 10. Fine. Now if you consider this equation that you have seen already, here molar mass of H2O2, it is 34 gram per mole. So you can easily calculate it. 2 oxygen means 16 into 2, 32, and 2 hydrogen means 1 into 2. So it is 34 gram per mole. But this molar mass will, this value will be required. Now at NTP, volume of 1 mole of any ideal gas, that we know it is always 22400, and you can also write it in terms of liter, which is 22.4 liter. Okay. So 22400 ml of O2, or you can say 1 mole of O2, that will be produced from 68 gram of H2O2. Why 68 gram? 68 because it is 2 moles. 1 mole is 34 gram. That means 2 moles will be 68 gram. So from 1 mole, from 2 moles of H2O2, you are getting 1 mole O2. That means 1 mole O2 obtained from 2 moles of H2O2, or we can also say it in a different way that this ml of O2 is obtained from 68 gram of H2O2. So 10 ml of O2, that will be obtained from 68 divided by this simple calculation into 10, and the value we are getting 0.03 gram of H2O2. Okay, so 22400 ml of O2 is obtained from 68 gram. From that you can calculate 10 ml of O2 will be obtained from 0.03 gram. But remember, this amount of H2O2 that is actually present in 1 ml of H2O2 solution, because that is the definition. When we say 10 ml of H2O2, that means from 1 ml of H2O2 sample you are getting 10 ml of O2. So 10 ml of O2, that is also equal to 0.03 gram of, sorry, 1 ml of H2O2 solution, that is basically containing this amount of H2O2, because this amount of H2O2 is the source of 10 ml of O2, and 10 ml of O2, according to that this definition 10 volume H2O2, it means 10 ml O2 is obtained from 1 ml of this solution. So we can say 1 ml of H2O2 solution contains 0.03 gram of H2O2. Now we are here doing the conversion to percentage strength. So we have to know what will be the amount of H2O2, that is a mass of H2O2 that you will be getting from 100 ml. So from 1 ml, if it is 0.03, from 100 ml, it will be 100 times more, that means 3 gram. So that is why the answer is percentage strength is 3%. Okay, so 10 volume is 3%. Now the reverse way we will see in the next class. Then when it is given 3%, that is the percentage strength, how you can convert it to volume. So the reverse calculation we will also see. But today we will end the session here. Thank you for listening.